Dear students, friends and learners, I am Dr. Shashank Shrivastava from the School of Engineering and Technology, IGNOU. So I was discussing with you the material science course which I am offering to you, and till now we have completed the unit 1, which comprised of 6 lectures, and from now onwards we will be discussing the unit 2, which is named as Engineering Alloys, Ferrous and Non-Ferrous, and it may consist of around 6 to 7 modules. So we start now. So we see in our lives that most commonly used solid materials are the metals, plastics and ceramics. Further, metals may be used in their elemental form like aluminium, copper and other things. Alloys are a combination of metallic elements and additives which are much smaller in quantity as compared. So we are talking about alloys now. And what are alloys? It's a combination of metallic elements, and there are certain additives also. Like suppose there is iron. So iron will be the main basic metallic element, and in addition to that there may be certain others like molybdenum and nickel and or many other smaller elements. So these small elements are in very small quantity and iron will be in large quantity. So this is the alloy. Alloy is the combination, but metal has to be there. Any one metal has to be there in an alloy. All alloys in which iron is the general base element are thus called the ferrous materials, and other alloys which don't have iron as the base element are known as non-ferrous materials. So now we discuss about the ferrous materials. Ferrous materials, both metal and alloys having iron as their base, are most useful for use in engineering machines and structures. And what is the reason behind that? Because of the wide range of properties they possess. So owing to the advance in steel technology and casting technique, ferrous metals are cast, shaped and machined in various shapes and sizes. So this you can see that ferrous materials, they can be changed into various shapes and they can be used in so many applications. Several standard shapes of sections are available commercially, which make the job of designer and constructor much easy. So these are some of the reasons why ferrous materials are so famous. So applications, again I am discussing with you some common applications which you can see in your daily lives. Like you can see trusses, bridges, ships and boilers. All these things are having the ferrous materials. For such construction, standard section and sheets of plates of steel are available. So for these things, sheets of the iron material or the ferrous material are used and standard sections are used. Other machine parts like shafts, gears, bearings, pulleys and other body parts of the various machines, they are made of steel, and there are certain processes through which they are made, like the forming, cutting or casting. So all these processes are there which you are taught about these processes in the manufacturing science also. So metal cutting tools, dies, punches, jigs and fixtures are also made in ferrous metal. So this is a very strong material, so it is used for the purpose of cutting also. So cutting tools are also made of ferrous materials, generally of steel, high carbon steel. One of the largest consumer of steel is the automobile industry. Nowadays we are seeing that different fibers are also coming in to replace this steel or the ferrous material because they are very strong, like the carbon composites and all other things are being talked about. But still nearly 60% of the weight of the car is steel. So that's why steel and ferrous materials are very much required. So we shall see a historical perspective also of this. So it is said that the first human effort in the direction of making tools was based upon the meteoritic iron obtained from meteorite that had struck the earth. So there are meteorites, you must have heard about them. Meteorites, like in Hindi we call that ulka pind. So they fall from the sky on the earth planet. So they contain iron. So that was the first use by the humans, and it happened around 3000 BC. Then in India, the well-known Ashoka column in Delhi, so many of you may have seen, was constructed about 4000 years ago. So this is also of the ferrous material, an example of that. The blast furnace through which the iron is produced, it was invented in 1340 AD, and it became possible to produce large quantities of iron and steel through this method. The future trend is to replace steel by plastics. So nowadays we are coming up with plastics in various machines and equipment, and fibers. So the target of this has been achieved quite a lot, mostly in the home appliances. The demand for steel is still level since 1965. Cost fluctuations in most metals have been controlled. The same is true for steel, whose cost is increasing at constant rate since early 80s. So let me tell you about the objectives of this particular unit, and I am giving you the whole objectives of the whole unit, not of one lecture. So you can note down that. So the first objectives are as such: to know about the production of iron and steel, then to know about the classifications and applications of steel, to understand how different types of steel are formed as alloy, then identify different constituents of steel and their effects on the properties of steel, then to know about the steel treatment. Further understanding of alloy steel and effects of alloying on properties, distinguish between steel and cast iron and properties and uses of cast iron, then to know about the alloys of copper, aluminium and their properties and uses, meaning the non-ferrous ones also, identifying the bearing materials, and identify creep resistant materials also. So now we start with iron and steel production. So what is the raw material that is required for iron and steel production? Basically there are three. The first one is the iron ore, the second is the limestone, the third one is the coke. So we know that iron as such does not occur in free state in nature. If somebody says that I want iron in the nature itself, then directly it is not possible. It occurs in the form of ores. But still it is very much abundant in the earth. About 5% of the earth's crust is in the form of various ores of iron. The principal iron ores are: number one, taconite. It's a black flint-like rock, so it is rock type. Hematite, it's iron oxide mineral. So iron oxide, there are different, meaning the combination of iron and oxygen. So it's iron oxide. Generally we see, say, Fe2O3. Then the limonite, which is also an iron oxide containing water. So the difference between limonite and hematite is that one is iron oxide without water, whereas the limonite is the one containing water. So when iron ore is there, it's not pure iron, so it needs processing. So now we discuss the processing of iron ore. So after it is mined, after the iron ore is mined, it is crushed into very fine particles, very small particles. The impurities are removed by various means. We know that there are certain impurities in everything. It's an ore, so we have to remove those to get the pure form of iron. So there are different methods. One is the magnetic separation method. And then it is formed into pellets, balls or briquettes using binders and water. So it is changed in the form of small pellets or balls with the help of, there are binders, different kinds of binders are there to stick it together, and water is also used for that purpose. Typically pellets are about 65% pure iron and 25 millimeter in diameter. So this is a kind of a standard, you can say. They contain 65% pure iron and their diameter is kept as 25 millimeter. The concentrated iron ore is referred to as beneficiated. So this is a term which is used, that if it is concentrated, the iron ore is concentrated, it is known as beneficiated. Some iron rich ores are used directly without pelletizing. So in some cases we don't use pellets, we are using them directly. Then next raw material was the coke. So now we can see the importance of coke. Coke is obtained from special grades of bituminous coal, which are heated in vertical coke ovens to temperatures of 1150 degrees centigrade and cooled with water in quenching towers. So this is a kind of process how coke is obtained. It is obtained from the bituminous coal, which is one variety of coal. There is the anthracite, there is the lignite, all those are there. You must have read also, but we don't need to go deep into that. we should know only this much, that coke is obtained here from the bituminous coal. Functions of coke in steel making we will see now. Number one is that it generates high level of heat required for chemical reactions to take place in iron making. So it generates the required amount of heat which is needed for the chemical reactions to take place in the process of iron making. Then it produces carbon monoxide, which is a reducing gas, and it helps to reduce the iron oxide to iron. The chemical byproducts of coke are used in making plastics and chemical compounds. So the byproducts which we are getting from coke are also used for making plastics and chemical compounds. And then the coke oven gases, when the coke is burned, then gases are also there. So these are used as fuel for plant operations and power generations, like in boilers also. Then the third raw material, that is the limestone. What is its function? We are seeing here now the function of limestone, that is also known as calcium carbonate as per the chemistry term. So it is to remove impurities from the molten iron. So the basic purpose of this limestone is to remove impurities from the iron which is being made, molten iron. And then it reacts chemically with impurities, acts as a flux which causes the impurities to melt at a low temperature. So this limestone causes the impurities to melt at a low temperature. Like for example, dolomite, an ore of calcium magnesium carbonate, is also used as flux sometimes. Then the limestone combines with the impurities and forms a slag. A slag is formed, which is light and floats over the molten metal. Slag is then subsequently removed. So when the slag is formed, it is lighter, so it floats over the molten metal, and from there it can be removed. The slag is later used for making cement, fertilizers, glass, building materials, rock wool insulation, and road ballast. So you can see even the slag which is obtained in this case of obtaining iron, we can see the slag is so much useful. It is used in so many purposes, like making cement, fertilizers, all those things. So now we discuss how this process happens, how iron is being processed, the iron ore is being processed, and we finally get pure iron. So this process actually happens in the blast furnace. So this is the blast furnace, you can see in the picture. And so it was first developed in the Central Europe, and the first furnace that began operation commissioned in 1621. Basic design comprises of a large steel cylinder lined with refractory bricks. Height is about 10-story building. So it is a very large steel cylinder, you can just visualize that, and it is lined inside with refractory bricks. Why refractory bricks? Because they act as the insulators. They prevent the heat of inside from leaking out. They prevent that thing. The three raw materials are charged into blast furnace by carrying them to the top and dumping them into the furnace. So the three raw materials which we talked earlier, that is the iron ore, the limestone, and the coke, they are charged from the top. Then the charged mixture is smelted in a reaction at 1650 degrees centigrade. So you have to note down the temperature at which this reaction is taking place. It is 1650 degrees centigrade with air preheated. So air is always required for any kind of combustion. So preheated air is used here, and it is preheated up to about 1100 degrees centigrade and blasted into the furnace. That's why its name is blast furnace. From here the name comes, because the preheated air is being blasted into the furnace through nozzles, or the nozzles are also known as stirrers. Main reaction is that of iron oxide with carbon, which produces carbon monoxide. So here the main reaction that is taking place is that iron oxide which is there is reacting with carbon, and it is getting reduced, and finally we get iron, and the gas which is produced is carbon monoxide. Preheating the incoming air is very necessary, because the burning coke alone does not produce sufficiently high temperature for the reactions to occur. So if the preheated air is not there, then this reaction will take larger time, because the sufficient temperature is not reached. So after this blast furnace process is over, then we do the collection process. So how it is done, we are seeing here now. The molten metal accumulates at the bottom of the blast furnace, while the impurities float to the top of the metal. So like we saw earlier that slag was going to the top, so here also impurities go to the top, whereas the molten metal is at the bottom of the blast furnace. So at regular intervals of 4 or 5 hours, this molten metal is tapped into ladle cars. So there are certain cars which are named as ladle cars, into that they are collected. Each ladle car can hold as much as 160 tons of molten iron. So that is the size of that ladle car, that it can hold about 160 tons of molten iron. The molten metal at this stage, now comes the chemical constitution, has a typical composition of 4% carbon, 1.5% silicon, 1% manganese, 0.04% sulfur and 0.4% phosphorus. So this is the chemical constitution of the iron that is coming out from the blast furnace. And remaining portion, these are the small elements. What is the remaining? The iron, pure iron. So that is how much it is, about, you can say around 94 to 95%. The molten metal that is collected is referred to as pig iron. Why we are using the word pig here? Because it comes from the early practice of pouring molten iron into small sand molds. So earlier practice was that there were sand molds and they were arranged like a litter of small pigs around a main channel. That's why its name is pig iron. The solidified metal is called pig and is used in making iron and steels. So after discussing the iron ore processing, we now move to the making of the steel. So steel was first produced in China and Japan in about, it is said, 600 to 800 AD. The process is essentially one of refining the pig iron obtained from the blast furnace. So how do we get the steel actually? We just refine the pig iron to get the steel. The refining of pig iron consists of reduction of the percentage of manganese, silicon, carbon and other elements, and control of its composition by the addition of various elements. So this is the process how we are getting steel. We have already got the pig iron and we do certain changes, like we do the reduction of certain other elements like manganese, silicon, carbon etc. So we are doing certain adjustments and finally we will get different kinds of steel. The molten metal from the blast furnace is transported into one of the 3 types of furnace. Again for steel making there is another kind of furnace. So molten metal from the blast furnace is taken up and transported into one of those. The steel making furnaces are known as the open hearth, electric and the basic oxygen one. So the first one is the open hearth furnace. Its name is open hearth and this name is derived from the shallow hard shape that is open directly to the flames that melt the metal. So it is a certain hard shape which is shallow and is open to the flames directly. So it was developed around 1860, the open hearth furnace, and it is being replaced now by electric furnace and by the basic oxygen furnace. Why? Because these newer methods are more efficient and produce better quality steels. So after the open hearth furnace, now we come to the electric furnace. Electric furnace was first introduced in 1906. The source of heat in this case is a continuous electric arc formed between the electrodes and the charged metal as shown in the figure. So here the figure is given and you can see that temperature as high as 1925 degrees centigrade are generated in this type of furnace. So here we see the electric furnace. You can see in the diagram the carbon electrodes, the leads that are coming into it, and at the bottom you can see the rammed hearth. It is somewhat hard shape and this is a different view, so we cannot see that, and the metal at the bottom is there, slag on the top of that is there. So this is called the direct arc electric furnace. There are 3 graphite electrodes, like I told in the diagram. These are the 3 graphite electrodes in direct arc electric furnace, and they can be as large as 750 millimeter in diameter and 1.5 to 2.5 meter in length. So length is around, you can say 1.5 to 2.5 meters. That means around 4 feet to around you can say 7 feet. Their height in the furnace can be adjusted depending on the amount of metal present. So it can go up or down depending upon the molten metal which is at the bottom. and also on the water of the electrodes. Okay, now the process about this electric furnace, we can see the steel scrap and a small amount of carbon and limestone are dropped into the electric furnace through the open roof. So there is an open roof at the top, and from there the raw materials are dropped inside. Next, electric furnaces can also use 100% scrap as its charge. So that is the advantage of that we can completely use scrap only. The roof is then closed and the electrodes are lowered. Like earlier I told that the electrodes height can be adjusted. So similarly here the electrodes are lowered after the roof is closed. Then the power is turned on and the metal melts within 2 hours. So this process takes only 2 hours, the melting process. The current is then shut off, the electrodes are raised again and the furnace is tilted. The molten metal is poured into a ladle like I discussed earlier. The collection car is known as the ladle, and here it is collected, which is a receptacle used for transferring and porting molten metal. Electric furnace capacities range from 60 to 90 tons of steel per day. So these furnaces can produce around 60 to 90 tons of steel per day. The quality of steel produced is better than that of open hearth or basic oxygen process. So out of the 3 kinds of the furnaces, this one gives the best quality of steel, meaning the electric arc furnace. Electric arc furnace capacities, as told earlier, it ranged from 60 to 90 tons of steel per day, and the quality of steel is better than the other ones. And this here in the figure is shown an indirect electric arc furnace. The first one which was shown was the direct electric arc. This one is the indirect one. As you can see in the figure, the electrodes are placed differently in this one as compared to the first one, which is the direct arc electric furnace. Then the third variety is also there, which is called the induction type electric furnace. So in the induction type electric furnace, it is shown in the figure, you can see this one is basically used for smaller quantities. It will not give like the earlier one 60 to 90 tons of steel. It is only for smaller quantities. The metal is placed inside the crucible, like you can see in the figure. The crucible is there, so metal is placed there, and this crucible is made of refractory material and surrounded with a copper coil through which alternating current is passed. So all the things are there. Copper coil is there for passing the current, and refractory is there so that no heat loss is there. The induced current in the charge melts the metal. These furnaces are also used for remelting metal for casting. So they are also used for the second process, that is remelting again for casting purposes. And the third furnace is the basic oxygen furnace, and it is the newest and fastest steel making process. So if you want steel at the fastest rate, then this furnace is the best one and the latest one. Typically 200 tons of molten pig iron and 90 tons of scrap are charged into a refractory lined barrel shaped vessel called the converter. So here the vessel is called the converter, and the mixture is that of 200 tons of molten pig iron and 90 tons of scrap. So then in the process, pure oxygen is blown into the furnace for about 20 minutes under a pressure of about 1250 kilopascal. So these are the conditions you can note down. That is, the pressure is about 1250 kilopascal, and it is done for about 20 minutes. And this is done through a water cooled lance, and it is shown in the figure. So there are the figures. Fluxing agents such as burnt lime are added through a chute. So here in the figure you can see the process in the basic oxygen furnace. The first figure is about the charging the scrap into the furnace, you can see in the figure. Then further the molten iron is being charged into the furnace. The third one is about the addition of the burnt lime. So burnt lime is also one of the raw materials. So the fourth one is about the blowing of oxygen, like I mentioned earlier. Oxygen is blown into the furnace. The fifth one is about how to collect, tapping the furnace. It is tilted and slag is at the top. And the sixth one is about pouring the slag into the ladle or the car. So continuing with the process, how it is done: vigorous agitation by the oxygen. See, oxygen was being blown into the furnace, so there is agitation due to that oxygen. It refines the molten metal through an oxidation process. Iron oxide is first produced. First of all, iron oxide is produced in this reaction. Then iron oxide further reacts with carbon in a molten metal and is reduced to iron. Carbon monoxide and carbon dioxide are also the products. The lance is retracted and the furnace is tapped by tilting it. The opening in the vessel is so provided that the slag still floats on the top of the molten metal as seen in the figure here. So in the figure you can see that the opening is such that the slag still keeps floating. It will not fall out. The slag is then removed manually by tilting the furnace in the opposite direction. So this basic oxygen furnace process is capable of refining about 250 tons of steel in just 35 to 50 minutes of time. So you can see within an hour we are getting about 250 tons of steel. And this steel is better in quality than the open hearth furnace, but not as high quality as the electric arc furnace. But it has still got low impurity level. High quality steels are processed into plates, sheets and various structural shapes such as I-beams and channels. So the I-beam gives us more strength. So this is used in various places like the railways and all. So all these are coming from this process only, the basic oxygen furnace process where high quality steel is being produced. And further what we do that we sometimes use vacuum melting also, because it produces very high quality steels as it removes gases impurities from the molten metal. Further we move on, we go on to the ingot casting. First of all, what is ingot actually? Ingot is the solid steel obtained from molten steel conversion. So it's the solid product that is obtained from the molten steel conversion. Ingot further processing happens and it is rolled into shapes and cast into semi-finished forms, and forging also takes place. So to remove the need for this ingot, actually continuous casting is also adopted and it improves the efficiency. We shall discuss it later. Molten metal is poured from the ladle into the ingot molds. Actually molds are made. Molds are a kind of shape or die you can say, in which the molten iron is being poured and it will take the shape of that particular mold and solidify there. So here is the definition, proper definition of molds. Molds are usually made of cupola iron or blast furnace iron with 3.5% carbon. They are tapered in order to facilitate the removal of the solid metal. So there is a certain kind of slope that is given, tapering is given, so that the solid metal that is being formed can come out easily. The bottoms of the molds may be closed or open. If open, the mold are placed on a flat surface. So if the bottom of the mold is open, then it is generally placed on a flat surface so that the this molten iron doesn't flow away elsewhere. The taper may be such that the big end is down. So the big end is kept down, meaning the end with larger area you can say is at the bottom, and with a lesser cross-sectional area one is at the top. The cooled ingots are removed or stripped from the molds and lowered into soaking pits. So this is the further processing that is taking place. Then they are reheated to a uniform temperature of about 1200 degrees centigrade for subsequent processing by rolling. Now rolling will take place and the temperature is around 1200 degrees centigrade. Ingots may be square, rectangular or round in cross section. So the cross section of this ingot actually may be of different shapes like square, rectangular or round, and their weights range from a few hundred kg force to about 40 tons. So now we will take up the effect of reactions on steel quality. So there are different reactions that are taking place inside the furnace. So what effect is it having on the quality of steel that we get from the furnace? So reactions during the solidification of ingot. First one, significant amounts of oxygen and other gases can dissolve in the molten metal during steel making. So oxygen and other gases are there which dissolve in the molten metal when this steel making process is taking place inside the furnace. As temperature decreases, the solubility limit of gases in metal also decreases. hence much of the gases are rejected. So as the temperature will go down, these gases will be rejected, which were first absorbed or dissolved. So the rejected oxygen combines with carbon, forming carbon monoxide, which causes porosity in the solidified ingot. So this rejected oxygen is now combining with carbon. So when it combines with carbon, it forms carbon monoxide, which is not a good thing because it causes porosity in the solidified ingot. Three types of steel are produced depending upon the amount of gas evolved during solidification, and these are killed, semi-killed and rimmed. So further we will see why these names are there. So the first one is the killed steel. So killed steel, it means that it is free of any oxygen. It is usually deoxidized steel. That's why its name is also like that, from which oxygen has been completely removed and porosity is also eliminated. The term killed comes from the fact that the steel lies completely quiet after being poured into the mold. So there is no agitation or no movement of the steel taking place, that the molten portion is there. So it lies completely still. That's why the name is killed. A fully killed steel is thus free of any porosity and blowholes caused by gases. So a killed steel has these properties, that it doesn't have any porosity and blowholes because all the gases including the oxygen have been removed. The chemical and mechanical properties of killed steel are relatively uniform throughout the ingot. So chemical and mechanical properties don't vary too much. Then the next one is the semi-killed steel. Semi-killed steel is partially deoxidized steel. So we saw in the killed one, complete oxygen removal was there. In this one, only partial removal is there. It contains some porosity due to this, generally in the upper section of the ingot, but has little or no pipe. No piping is taking place, but still porosity is there and scrap is reduced. Although piping in semi-killed steels is less, it is compensated for by the presence of porosity in that region. So we can see that the negative effect of piping in semi-killed steel is not there, but the second negative effect is coming in because of the porosity. So it's not giving us such a benefit as such. Semi-killed steels are economical for deoxidation process, that is quite costly. Then the third one is the rimmed steel. So in this case, there is very low carbon content in the steel. It is about only 0.15%. Evolved gases only partially killed or controlled by the addition of elements such as aluminium. So here aluminium is added, but still the evolved gases are only partially killed. The gases form blowholes along the outer iron of the ingot. So the ingot, the outer portion, so there are blowholes, and that's why this name is rim. Like the rim, if in a vehicle you see in the motorcycle, the rim is there. So or the rim, the tire is there. So that kind of shape is there. That's why the name is rim. Blowholes are generally not that problematic unless they break through the outer skin of the ingot. So blowholes can be tolerated unless they are breaking the outer skin of the ingot. Rimmed steels have little or no piping. Again, no piping effect is there, so this negative thing is going out, and they have a ductile skin with good surface finish. So rimmed steel has got very good surface finish. The blowholes may break through the skin if they are not controlled properly. So the blowholes have to be controlled, otherwise they may break through the skin, and then the negative effect comes in. Impurities and inclusion tend to segregate toward the center of the ingot. So in this case of rimmed steel, the impurities and all kinds of inclusions are moving towards the center of the ingot. So the products made from this steel may be defective and should be inspected. Very necessary to inspect those things. So further we discuss refining now. Since there are impurities and inclusions and these cause an adverse effect on ferrous alloys, so refining needs to be done. The properties and manufacturing characteristics of ferrous alloys vary due to the above impurities. Due to these impurities, the properties of the ferrous alloys vary a lot. The removal of impurities is known as refining, much of which is done in melting furnaces or ladles with the addition of various elements. To meet the increasing demand of cleaner steel, refining is particularly important in producing high-grade steels and alloys for high performance and critical applications such as in aircraft. Moreover, warranty periods on several machine parts such as shafts, camshafts, crankshafts for diesel trucks, etc. These can be increased significantly using higher quality steel. So refining is a must. The trend in steel making is for secondary refining in ladles and vacuum chambers. New methods of ladle refining, injection refining generally consist in melting and processing in a vacuum. Again, the vacuum thing is coming, like I told earlier, it helps to remove the various impurities in the gases. Several methods of heating and remelting have been introduced for their efficiency and cleanliness. So there are different methods for heating and remelting. These are normally used in controlled atmosphere, and some of the methods names are as such. The first is electron beam melting, the second is vacuum arc remelting, third is argon oxygen decarburization, and the fourth one is the vacuum arc double electrode remelting. So these are different methods through which we do the remelting. Now we discuss about the continuous casting. As I told earlier that we can get rid of the ingots by using continuous casting. Now we can discuss that. So why do we need continuous casting? Because the traditional method of casting ingots is a batch process. It can give you the final things or products in batches only. It can't be a continuous thing, so we have to wait for some time. Each ingot is stripped from its mold after solidification and processed individually. So again, it's very time taking and tedious process. Additionally, what happens in ingots that defects like piping and microstructural and chemical variations are present throughout the ingot. So for that purpose, continuous casting is there, and we can now discuss the process of that. So the figure is here for continuous casting. The molten metal in the ladle is cleaned and nitrogen gas through it is blown for 5 to 10 minutes to equalize the temperature. So nitrogen is an inert gas, that's why it is being used, or argon can also be used because it doesn't react to the iron or the steel by itself. It doesn't react, and it gives an inert atmosphere. It just is used to equalize the temperature. The metal is then poured into a refractory lines intermediate pouring vessel. This is the further process, and this vessel, the intermediate pouring vessel, is known as the tundish, where impurities are skimmed off. So in this vessel the impurities are removed. The tundish can hold as much as 3 tons of metal. So it is as big, you can see it can hold 3 tons of metal. The molten metal then vessels or flows through water cooled copper molds. There are copper molds, you can see in the figure, and then it begins to solidify as it travels downward along a path supported by rollers. So you can see at the bottom there are rollers which are supporting this equipment. So before starting the casting process, what happens, a solid starter or dummy bar, a kind of a bar, is inserted into the bottom of the mold, which you can see in the figure. So it is known as the dummy. The molten metal is then poured and freezes onto the dummy bar. So the molten metal is poured, is freezing on the dummy bar. It is given in the figure also. The bar is withdrawn at the same rate the metal is poured. So the rate of withdrawal of this bar at the bottom is same as the rate of the metal which is being poured from the top. The cooling rate is such that the metal develops a solidified skin to support itself. So a certain cooling rate is given. It's very important because the metal is providing to itself a solidified skin such that it can support itself. So that rate of travel downward, the speed is 25 mm per second. The shell thickness at the exit end of the mold is about 12 to 18 mm. And we do additional cooling by providing water sprays along the travel path of the solidifying metal. The molds are generally coated with graphite or similar solid lubricants to reduce the friction. We need to reduce the friction there, and adhesion also, so that we can easily remove that. And vibration of molds also further helps to reduce the friction and adhesion tendency. The continuously cast metal may be cut into desired lengths. So what we are obtaining at the end, we can cut them into desired lengths by shearing or touch cutting mechanism, or it may be fed directly into a rolling mill for further reduction in thickness. So all these things are possible in continuous casting. We can go directly from this process to another process. Whether the steel is obtained in form of ingots, stationary molds, or in form of slab from continuous casting process, it is converted into blooms, billets and slabs. So whatever may be the process, whether it be ingot type or the continuous casting type, these are the things in which they are converted, which are known as blooms, billets and slabs, which now I am discussing with you. So subsequent hot roll products are described as follows. Blooms. Blooms are what? Beams and angle sections. Rails, bars of different sections. Like you may have seen in common life also, there are beams in buildings and there are rails on the railway track. So all these are known as the blooms. Billets. Billets are a different form of this material. These are wire nails and wire mesh, or they are pipes and tubes. Different uses are there and different names are there. Then the final one is the slabs. Like slabs, plates are there, strips are there, and further cold rolled, and they are for reducing the thickness. So these are the three types: blooms, billets and slabs. So in this session now we have discussed about the ferrous materials, how iron ore is processed and we get the pure iron, and further we have also seen how steel is also being made. So these things we discussed in the lecture, and further things we shall discuss in the upcoming sessions. Thank you very much.